Today we also discuss on important topics which is related to measure theory. We also discuss today. This one is translation invariant. Okay, how we discuss it, we write it. This one is now. Here MB translation invariant. Okay, translation invariant. That is if a set for which M is defined. If a set for which M be defined. Okay, and if e plus y be the set this one x plus y where x belongs to it, obtained by replacing each point x on E, obtained by replacing each point x on E, each point x on E. Okay, by the point x plus y, then m e plus y equal to me. Okay, then what happened? If we transfer some measure with translation invariant when, that means if E be a set for which M is defined, E be a measurable set, and E plus Y be the set, this one x plus y, okay, where x belongs to E, obtained by replacing each point x on E by the point x plus y. Then what happened? Then M E plus Y equal to M. Okay, this one is the translation invariant. Okay, on measure. Now we're also going to discuss one important proposition right now. Okay, this proposition is the outer measure. Okay, the outer measure of an interval be its length is its length. Okay, we'll also discuss this one now. Okay, outer measure of an interval is its length. Also prove this one. This one too lengthy, but we also discuss too easily. Okay, right now proof. Let's start this one. We begin with the case in which we have a closed finite interval. That means we first consider a closed finite interval. Okay, AB. We considered it. Okay. Then since the open interval a minus epsilon b plus epsilon contains closed A. For each positive for epsilon greater than 0, we have m star, this one closed AB, less than equal to L of this one. Okay, length of A difference epsilon and B plus epsilon equal to what? Equal to B minus A plus 2 epsilon. Okay, for each positive epsilon. That means this one is happen. So we must have what m star this closed AB less than equal to B minus A. Okay. Now what we write? We only have to show. Now we have to show what m star this AB greater than equal to B minus. Okay. So how we show this? Okay. We erase that portion and going to further discussion of that. Then one portion is done. Okay. So we erase that portion. But this is equivalent to showing that, okay, that is if IN be any countable collection of open interval, be any countable collection of open intervals be any countable collection of open intervals covering closed AB. Okay, then what happened? Then summation of LIN greater than equal to B minus A. Okay, this marked as 1. If IN be a countable collection of open intervals covering this closed AB, then summation of LIN greater than equal to this. Then by the Harnaveral theorem, any collection of open intervals covering this AB contains a finite subcollection. Okay, that also covers closed AB. Okay, and since the sum of lengths of finite subcollection is obviously closed AB, and since the sum of the lengths of the finite subcollection is not greater than the sum of lengths of original collection, it suffices to prove that first one. What happened? Okay, That means per Hannibal theorem we also get a finite subcollection that also covers AB. And then we also see that the sum of the lengths of finite subcollection is not greater than the sum of the original collection. It suffices to prove that what? First, for finite collection, In that covers for finite collection In, then that covers AB. Okay, and since A contained in union of In, okay, A contained union of In, then there of the one of the In, then one of In then contains A, okay. Then let this be the interval, this one. Let this interval be A1 B1, then A1 less than A less than B1. Okay. Now we're going to with that if B1 less than equal to B. Okay. If B1 less than equal to B, then what happened? Then B1 belongs to AB. Okay. And since B1 does not belongs to this one, since B does not belongs to this one, then there must be an interval A2. Since B does not belongs to A1 B1, okay, then there must be an interval, okay, an interval A2 B2 which satisfies what? If B1 less than this one is since sorry, then here B1 does not is not closed, this one is open, B1 does not belongs to this, then there must be an interval A2 B2, okay, in collection in the collection In such that what? B1 belongs to this A2 B2, okay, B1 belongs to this A2 B2, that is A2 less than B1 less than B2, okay. Then we erase that portion and continuing in this way, okay. What happened? Then continuing in this fashion or in this way, we obtain a sequence. A1 B1 A2 B2 AN BN, or here we write AK BK, okay, from the collection In, okay, such that AI less than equal to Vi minus 1 less than equal to Vi or less than Vi, okay. Then what happens? then obviously we get, since I n be a finite collection, okay, I n be a finite collection, then our process terminate, our process must terminate. Okay, then what happened? With some interval ak, with some interval ak bk, then what we get? Then if b belongs to ak bk, okay, then the ak less than b less than bk, that's what we get. Thus summation of lin or ik equal to what? Greater than equal to summation of l ai bi, okay, equal to bk difference ak, thus bk minus 1 difference ak minus 1 plus b1 difference a1 equal to bk difference ak difference bk minus 1, okay, difference ak minus 1 difference bk minus 2 a2 difference b1, okay, here minus a2 difference b1 minus a1, okay, this greater than equal to bk difference a1, okay, this greater than what? This greater than this one, okay, then what happened? Since ai less than bi minus 1, okay, so this one happened. Then what we get? We get bk greater than b and a1 greater less than a, okay, so we have bk difference a1 greater than b difference a, okay, when summation of lin greater than b minus a, okay, this shows that n star of ab equal to b minus a, okay, so we also do this one again, and if this one is another length, then what happened? Okay, that means this one is closed interval, then this one is happen, okay, we prove this one. Now we're going to, if any interval, then what happened? Okay, so if I is any interval, if I is any interval, then what happened? Okay, if I be any interval, then any finite interval, any interval which is finite, then what happened? Then giving epsilon greater than 0, okay, and there is a closed interval, closed interval, there is a closed interval J subset of I such that Lj greater than Li difference epsilon. Okay, hence what happened? Hence Li difference epsilon less than Lj. Okay, equal to m star j less than equal to m star I. Okay, less than equal to m star I closer. Okay, equal to what? Li closer. Equal to what? Equal to Li. Okay, then what happened? Obviously we check if I be any interval. Then what happened? There is a closed interval, and this closed interval that means shows that, okay, this closed interval L of I Lj greater than Li difference epsilon. Okay, then this one happen. Okay, so what we get from this, so for epsilon greater than 0, Li difference epsilon less than m star I less than equal to Li. Okay, so we get m star I equal to Li. Okay, then if I be any finite interval, then this one is done. Okay, now we getting another one. Okay, we write here, if I be any infinite interval, then what happen? If I be any infinite interval, then given any number delta, there is a closed interval J subset of I with Lj equal to delta. Hence what happened? And m star I greater than equal to m star j equal to Lj equal to delta. Okay, so since m star I greater than equal to delta for each delta, m star I equal to plus infinity equal to L of I. Okay, if I be any infinite interval, then giving any number delta, there is a closed interval J subset of I with Lj equal to delta. Hence m star I greater than equal to m star j equal to Lj equal to delta. Then m star I greater than equal to delta implies that what? M star I equal to plus infinity equal to Li. Are you understand or not? Obviously understand. Giving any positive number if we write beta. Okay. Then this one is happen. Now we're going to write about some lemma. We also prove this one. Okay, we also prove the outer measure of an interval equal to what? Equal to length of this interval. How we prove? We first consider one closed interval, then we see about that this closed interval are, that means length of closed interval equal to outer measure of this. Okay, we also prove this one. Then obviously we use here High-Navarro theorem. Okay, obviously then High-Navarro theorem we use, and then obviously done this, and obviously consequently we find a finite, that means collection which contains this AB. Now we're going to, that means in this way we also prove this one. That means the outer measure of an interval its be its length. Now we also prove some lemma. Well, erase that portion now. Okay, this lemma is tell us that if m star e be 0, then e be measurable. Okay, we're also going to be this lemma. Just write this lemma now. Okay, this lemma statement is if m star e equal to 0, then e be measurable. Then e be measurable. Okay, m star e equal to 0, then e be measurable. Let a be any set, then a intersection e subset of e. So m star a intersection e less than equal to m star e equal to 0. Okay, then what happened? Also a subset of a intersection e delta equal to what? So m star e greater than equal to m star a intersection e delta equal to what? Equal to m star a intersection e delta plus m star a intersection e. Okay, then what happened? Okay, then we also see about that m star a intersection e plus m star a intersection e delta less than equal to m star a. Okay, then what happened? Then we also see that, okay, e be measurable. Okay, because this less than equal to this one, e delta here we considered e complement. Okay, and obviously m star e less than equal to m star a intersection e plus m star a intersection e delta. Then we find here which one. Okay, why this one we find, and this one why? Since a equal to a intersection e, okay, union a intersection e delta, then m star e less than equal to a intersection e plus this one, because subadditivity property. Okay, here e delta be the complement. Okay, here e delta be the complement. So what we get? We get EV measurable. Okay, then m star e equal to 0 implies that EV measurable. Okay, also erase that portion now and going to another discussion of that. Okay, but today we also not discuss more. Today we stop here. Okay. And also next class we also discuss more topics.